continue with the last talk today. So I will introduce Amilcar Pacheco from the UFRJ. He will talk about towards a formulation of the BSD conjecture in chattering speed. Okay, go, Amilcar.
Thank you very much. Thank you for the organizers for the opportunity, and I would like to congratulate them for the nice talk, for the nice Congress. This is joint work with Marc-André, Université Paris-Cité, and it started. Let's start from where it all starts. In 1966, John Tate gave a Bourbaki exposé where he proposed a geometric analog of the Birch and Swinnerton-Dyer conjecture. So in the first case, when you have a number field and an abelian variety A defined over K, and you take a finite subset of places of K, and you choose it to be sufficiently large so that your abelian variety has good reduction outside S. Well, when you take a reduction modulo a prime, you can get either an abelian variety or an extension of an abelian variety by a linear group, which is a product of GMs and GAs. But we're excluding those primes. And we look at the OKS integers, and the fiber is just the product over the residue field kappa V, which is a finite field with NV elements, and we say the dimension of abelian variety is D. So if we go back to Weil, since we're looking at something defined over a finite field, we have an integral, a polynomial with integral coefficients, which is written as a product like that, which has a functional equation. When you invert the variable, you multiply by the number of points modulo V to the power D and T to the power 2D, so that all the roots have absolute value half of the cardinality of the residue field. And this polynomial is characterized by giving the product with the alpha IVs to the power m is just giving the number of rational points of an extension of degree m of the residue field. And this way we can define, should I say, restrict Euler product, because we are finding primes of bad reduction, as the product of the inverse of the polynomial computed at the cardinality of the residue field to the minus S, where S is a complex number with real part greater than 3/2. And this converges since it's dominated by the zeta function of the number field. Well, we go back to prehistoric times, K being a number field, then the set of K rational points of the abelian variety is a finitely generated abelian group with rank, say, R. So the weak conjecture tells you that when you look at the order of your L function at S equals 1, it should be equal, which we call the left-hand side analytic rank, it should be equal to the algebraic rank. So far, so good, but we can say even more. We can conjecture even more. We can conjecture what is the special value, what's the first term on the Taylor expansion. So we define the mysterious group, the Tate-Shafarevich group, which is the kernel of the map where you plug in the cohomology of K with A with respect to K, and the product of the cohomologies with respect to the places. And you have the Jew or abelian variety, pick 0 of A. And we define an Nehon-Tate pairing between the K rational points of A and the K rational points of the Jew variety. we take a basis of both finitely generated groups, modulo torsion, NT means non-torsion, and we define the regulator as the absolute value of the determinant of the Nernst-Tate pairing. And of course, there is a hypothesis missing there, which is the finiteness of the Tate-Shafarevich group. No, because we're taking just the smooth part. Huh? You're not considering the product, the bad primes. If you plug in the bad primes, then you have the Tamagawa number. So if you take the complete our function, what you have is the order of Shah, the regulator, the Tamagawa number, Q to the D, something like that, 1 minus G. G is the genus of the base in the geometric case. Let's erase this for a moment. And the denominator is the same thing, right? So, since at least Weil, we usually translate things we don't know about number fields to things that we should know about function fields. Which are finite extensions of a one variable function, a rational function field over a finite field FQ. So you have the same result as before, but with some power of Q here. Right? In the Bourbaki lecture of Tate, they start by defining a geometric analog of this. So he takes the function field of a smooth characteristic curve defined over a perfect field of characteristics P, and you define similarly the Tate-Shafarevich group, but now in terms of the closed points of your curve. Everything works fine. And Michael Archie proves that as long as you have a proper morphism where all fibers have dimension 1 and X is a surface, a regular surface, and the geometric fibers are connected and the generic fiber is smooth, if the fibration admits a section, then you have such an exact sequence relating the Brauer group of the base, the Brauer group of the surface, and the geometric analog of the Tate-Shafarevich group. And here this is done. A is the Jacobian variety of the generic fiber of that morphism. Moreover, if your curve's complete, then Brauer of the curve 0, so that you can look at the Tate-Shafarevich group as a Brauer group. Well, I should, before I go to the next slide, I should briefly write about what is the status of the Birch and Swinnerton-Dyer conjecture when C is a curve. Well, it started from that paper, the Artin-Tate conjecture, which is the case where A is a Jacobian, and they treat not the whole conjecture, but the L primary part for L different from the characteristic, and this was done by James Muni. Then there is a result of Bauer, where he treats the P primary part But he pays the price of assuming that A has everywhere good reduction. Now the next is Schneider, where he treats the L primary part for abelian varieties. And the most general result is due to Kato and Trian, which they do the whole conjecture. But the main point is that the finiteness of the L primary part of SHA implies the whole BSD conjecture, not only the conjecture about the rank, but the conjecture about the special value. And
something about their proof? Like, do they prove some analog conjecture?
no, they just prove that it suffices to prove that for some L, yeah. Huh? Yeah, the main problem is that they have to, an abelian variety is always potential semi-abelian. And they have to extend crystalline methods to the situation of semi-abelian reduction. So they use at some parts symptomic cohomology and the other part the generalization of crystalline cohomology in the sense of log geometry. And that's the main difficulty to obtain the P part of the conjecture. So in a way, what they do is extend Bauer to the case of semi-abelian. Yeah, it's an extension of Bauer to the semi-abelian to the case of semi-abelian reduction, and then you do some descent theorem to go to the original field. You're welcome. Now, a student of Bauer, Timo Keller, student of Schneider, Keller, he addressed some years ago the extension of Schneider's result to the case where your base is no longer a curve, but any complete variety defined over a finite field. But actually, he did not use the whole L function. He just used the components from H0 and H1. Since the main difficulty is, as in Kato-Trian and Bauer, the P part, what Marc-André and I thought was, what would be the approach for the P part? And it turned out that an ancient, from the 80s paper of Milne, he introduced a cohomology of certain sheaves linked to log differentials. It was also studied by Luc Lizzi, and the story goes like that. You start with a smooth, complete, geometrically connected variety of dimension dx, and you take an abelian scheme of dimension g over this variety. Then you have the sheaf of relative differentials, omega r of ax, and the kernel of the differential. We define the sheaf nu r ax as the kernel of the Cartier operator This is an operator introduced by Serre in the 50s. The main part is that it fixes log differentials. So this sheaf is the kernel of the Cartier operator acting on the differentials which are 0. by D. It's locally generated as a product when we take the power R by a wedge product of R logarithmic differentials. And then the Witt vectors come into place. So for each n greater or equal 1, we take the sheaf of Witt vectors of length n of the sheaf of differentials. This was again introduced by Serre in the 1950s. And we define a D-log map to Wn omega 1 of Ax by just taking the logarithmic differential of the first coordinate, and we define the new R Ax as the subsheaf of the sheaf of Witt vectors over the relative differentials generated by the wedge product of R F1 up to Fr by the D-log map. And both these sheaves taking n to be variable, they form a projective limit, and we denote by W infinity omega R of A over X and W nu R infinite A over X, the corresponding projective limits. Right? This is just language so far. Any questions? Well, the starting point, what I call Witt, Hodge-Witt cohomology, is that if you take the ith direct image of our sheaf, which is defined over A, first to X, and then its jth direct image to spec K, what we get is a sheaf which can be represented by a unipotent algebraic group, which I denote like that, which has the property that its set of k-bar rational points corresponds to the, when I don't specify the cohomology, it means that I'm taking a tau cohomology. This was done by mu in the absolute case, meaning x over k, and here we do in the relative case of an abelian scheme. So now we have to translate the tau cohomology into crystalline cohomology. So we take the sheaf of infinite vectors over the algebraic closure of our field K, and we take K bar to be the fraction field of such ring, and we have a topos, meaning we have the topos is the set of sheaves over X bar thought as defined over W bar. And if we define script X bar as essentially, topologically, is the scheme X bar, but the sheaf that we get is the sheaf which is obtained from the structural sheaf by taking the ring of Witt vectors of infinite components. And both of them have structural sheaves in the sense of crystalline cohomology, and we have a morphism of topoi from the sheaves of the, say, abelian scheme to the sheaves of the variety. And it admits derived functors, and also this morphism of topoi admits an adjoint morphism going the other way, but it doesn't matter here. So the groups which we shall be interested in are the groups in the crystalline cohomology where I take the ith direct image of phi cris on the structural sheaf of the abelian scheme. And the absolute Frobenius of the base field can be lifted to an automorphism of W bar, which is the ring of Witt vectors of the algebraic closure of K, and we denote by alpha AJI alpha its eigenvalues. The next definition comes from Cato and Bloch, where they define, again in the absolute case, like a variety over K, but I translate it into the relative case of an abelian scheme. So I define an abelian scheme to be ordinary if the cohomology coming from logarithmic differentials, when extended to the Witt vectors, is the same as the cohomology of the whole sheaf of differentials when you take its Witt vector, its Witt ring of infinite components. And one of the main points of our translation says that if your abelian scheme is ordinary, then you translate cohomology of logarithmic differentials, which is an étale cohomology, into crystalline cohomology in that way. If you take the differentials to the power r, you take the rth derived functor of phi Cris acting on the structural sheaf of the abelian scheme, more or less like that. Well, we have to introduce some more notation. Suppose you have a morphism of ZP modules. We say that's a quasi-isomorphism, which has nothing to do with complex. It's just to say that its kernel and its co-kernel are finite. And we denote by ZF the quotient of the number of elements of the co-kernel by the number of elements of the kernel. The absolute Galois group obviously acts on this cohomology group of logarithmic differentials by acting on X. So we can have a map from the G invariants of this group to the G co-invariants, and we denote this map by FJR. Actually, we shall be interested in the case where R is 1. So adapting a result of mu, we find out that the characteristic polynomial of Frobenius on the sheaf of logarithmic differentials can be expressed in that way, where the alpha j, the A JR alpha are the eigenvalues of sigma acting on the corresponding crystalline cohomology. So you see that here we have the rth logarithmic differentials, and here we have the rth right-derived image of phi Cris acting on the structural sheaf. So again, mu does this in the absolute case, and we can translate that to the relative case. Now we have an analog of a conjecture of Tate. So if we look back, these two sheaves have weight J minus R. So if I take R equals to 1 and J not 1, both will have non-zero weights. Therefore, one is not even a root of the characteristic polynomial, because since the weight is non-zero, it's q to the some power. Then an analog of a conjecture of Tate, which is again appears in the text of Mune for the absolute case, that 1 is not a root of the minimal polynomial of Frobenius acting on the first cohomology group of the differentials omega nu 1 and infinite of a bar over x bar. This allows one to actually compute. Remember that ZF is, when I look at the map, it's the cardinality of the co-kernel by the cardinality of the kernel. This allows both us and mu, we are in the relative cases, in the absolute case, to compute the Z of fj1. First of all, since this group, when j is different from 1, has non-zero weight, then it's always the case that z fj1 is defined, and z of f11 is defined if and only if this analog of Tate's conjecture is true. So in any case, we can compute the value of z of fj1 in terms of the eigenvalues of sigma acting on the crystalline. Remember that these are the eigenvalues of sigma acting on the crystalline cohomology group up there. And an information which comes from the algebraic group, which represents the sheaf phi star nu 1 infinite ax. And another information, the order of p of the eigenvalues are the slopes of the corresponding cohomology group. So it's something that's in practical. It's not very practical. In the text of Milne, he only computes in the absolute case for very simple examples, but still, it's a theoretical information. Now we go, finally, it's analytic number theory talk. There should be an L function. So remember that I am dealing with the case where I am in an abelian scheme, so we have everywhere good reduction, and the L function is expressed in that way. We define, obviously, the analytic rank as the order of vanishing when we replace the variable by q to the minus s at s equals 1. Algebraic rank is the rank of ax, which is the same thing as the rank of the rank ax is equal to the rank of ak, where A is the generic fiber. So it's an abelian variety over a function field of a variety. Both étale cohomology and crystalline cohomology are Weyl cohomology, so we have an equality between the characteristic polynomials. And using an analog of the Lefschetz trace formula in the context of locally free crystals due to a test, where am I? We can rewrite it as an alternate product of polynomials, where each polynomial is given in terms of the crystalline cohomology, and using our translation between crystalline cohomology and the cohomology of logarithmic differentials, we can write it in terms of this étale cohomology group. Now we discuss some rank formulas. We start by observing that since we are in the case of an abelian scheme, the Picard functor is represented by a sheaf which can either live on the FPPF site or on the tau site. But when we take the PN torsion of this sheaf, it can only be viewed in the FPPF site. But we have a projection morphism from the FPPF site to the tau site, and we shall denote the image of the subsheaf PIC0x AX of AX by AT. And this gives us an isomorphism for each n of the direct image of the PN torsion point of PKX with ATPN. And we define like a Tate module as the projective limit. But we're translating some information from FPPF to étale. The main thing is that we produce an exact sequence so that our main object is very close to being the p-adic Tate module of the Jew or abelian variety, except that there is a kernel here which depends on the logarithmic differentials of the base variety. When we take G invariants and we extended everything to the k-bar is the fractional field of W-bar is the ring of bit vectors of the algebraic closure of small k, we get such an exact sequence, so that you can read the rank of the Tate module in terms of the ranks of the sheaves which come from logarithmic differentials. So you get an equality. The rank of the sheaf that we're looking for will be the sum of the rank of the base sheaf plus the rank which comes from the Tate module. So if we start with an ordinary abelian scheme, the analytic rank will be at least the rank of the H1 of the bit vectors of logarithmic differentials, which will be, by the previous slide, at least the rank of the H1 of the p-adic Tate module. Moreover, this inequality is an equality if and only if F11 is an isomorphism, and by a previous result, oops, I'm going the other way around. This is equivalent to the analog of Tate's conjecture being true. In that way, if we plug everything together, when we have an ordinary abelian scheme, and for every j from 1 to 2d, in the case where j is equal to 1, we have to assume the analog of Tate's conjecture, the same simplistic conjecture. We can compute the z of F11, which is by definition this quotient, the quotient of the number of guys which lies in the G invariant subgroup divided by the quotient of guys which lie in the co-invariants. This can be expressed in terms of our polynomial, which gives the L function, the value of our polynomial at q minus 1 at p, times the information which comes from the unipotent group, the dimension, and the slopes of the crystalline cohomology. The next point is to what is the Tate-Shafarevich group in general? Well, we define, actually, Keller defined in an ad hoc way as the H1 et al. Of xa. The abelian scheme can be viewed either as a sheaf on the smooth locus, in the smooth side, or on the tau side. And he proved the geometric definition, the tau definition, coincides with the usual definition in the case of Jacobins. But for us, the only thing that we care is that it will be the first tau cohomology group of the sheaf given by the abelian scheme A. So since we are dealing with an abelian scheme, the map is proper and smooth, so we can identify this cohomology group with the corresponding FPPF cohomology group. And working with FPPF cohomology, then we have, in general, we don't have the surjection here, but then we have a map coming from the analog of Kummer. When we have FPPF, we can we can have surjectivity here, which we couldn't if it were just a term. So we have such an exact sequence, and it can be proved that the PPF cohomology H1 of the PN torsion points of the abelian scheme will be the same thing in the tau context. Remember that this guy is the direct image of, by the changing of sites of the usual PN torsion point of the abelian scheme. And taking the projective limit, we can write the cohomology of the Tate module in the usual sense of PPF cohomology in terms of this outer sheaf in a tau cohomology. So in the end, we get an exact sequence like that, and we look at this p-adic Tate module of the Tate-Shafarevich group. Actually, there should be X. And this guy will be 0 if and only if the P infinite part of the Tate-Shafarevich group is finite. So we have an isomorphism at delta if and only if this P primary part of the Tate-Shafarevich group is finite. So we have the following result, which organizes things a little bit and goes in the direction of the Birch and Swinnerton-Dyer conjecture. If you start with an ordinary abelian scheme, then the analytic rank will be equal to the algebraic rank if and only if the conjunction of the three following assertions hold. The first one is the finiteness of the P primary part of SHA. The second one is the semi-simplicity conjecture at the prime P for H1. And the third, which looks a bit strange, is to ask that the H1 of the sheaf of logarithmic differentials on the base should be ZP torsion. But morally, this guy should, this does not have a sense. This is just an Milne defines this H2 as this guy. But this guy resembles a Brauer group. And in some sense, we should expect torsion on the pre-primary part of Brauer group. So in that sense, that third hypothesis is not that awkward. So the equality of the ranks will be the same thing as SHA, the P-primary part of SHA being infinite, the semi-simplistic conjecture holding, and should say Brauer P being torsion. With this said, we can, under the three conditions so that the analytic rank and the algebraic rank are equal, we can compute the special value of the L function in terms of the cohomology groups coming from the logarithmic differentials. In fact, here it's the Witt vector. There is an infinite which is missing both fractions, and we have a power of P which depends on the algebraic group representing our sheaf and on the slopes of the crystalline cohomology. And this guy is the sum of all this information that we had before for every J. Now, we want to be near the original thing. So, once again, we start with an ordinary abelian scheme, and we suppose that the P-primary part of SHA is finite, the semi-simplistic conjecture holds for P, and Brauer P is torsion. Then we almost get what we should expect. Let me write what we do expect, what should be the right thing. If we look at the case of curve, the right thing would be the order of the p-primary chart of Shah, some object real, which reminds you of a regulator, and then here you have the order rational. So if we look back at that formula, this guy here should be the number of p infinite points of A which are k-rational. Shah is there, although that Shah is completely different from that. That's just the H1, and we do not know whether this formula extends other than the case of a Jacobian fibration. And what is 8LP? 8LP is the hard Lefschetz defect. Let me just write it. We have an analog of Lefschetz defect, and it shows in this case that when you go from H1, moment. Okay. In general, you have H1x phi lower star nu 1 infinite AX non-torsion part injecting on H2d minus 1 x phi star nu 1 infinite AX non-torsion with finite co-kernel, so HLP is the order of the co-kernel. It's called the integral hard Lefschetz defect. So if everything would be over, instead of being, that's a ZP essentially, if it were over QP, it would be an isomorphism. So what we're missing here is this other information. But what I want to conclude is with the possible formula for the whole the whole leading term of the function. So here you have a regulator in the sense that I had for an abelian variety over a number field or a function field. You have a regulator given by the set of sections, which will be the same thing as the set of rational points. And using some result of Gaber's where the contribution, I'll use the results of Keller for every L. And for most L, the contribution will be 0 due to a result of Gaber. And we end up with something like that for the whole special value. Now I'm putting the hat because it's like working with z hat when I put all the z out's together, and times divided by the torsion of the joule. Then comes a mysterious H2. And then comes the product of the invariants over the co-invariants. So we have here the same thing with G, the lower part, to the power 1 minus 1 J plus 1 times a power of P, which gives the information on the algebraic group representing such objects and the slopes of the crystalline cohomology. So this should be the final formula. So you see that when you specialize to the case where the dimension of the base is 1, this will be that group. Well, when you look at the P part, and this product will no longer be considered. So it will be trivial. So it's compatible. Of course, when I look back at the original thing, we're just doing Bauer. We're not doing Cato and Trian. The next step would be to work over semi-abelian scheme, which is the generic situation. But the semi-abelian scheme is not proper. So you can compactify it. One way to compactify it is to use the moduli. So if A bar, lower bar, is the moduli of abelian varieties with structures, etc. And here we have the generic one. These guys go into something compact, which goes into the compactification of this object. And then we can define, so we have our abelian scheme here. It goes to the open part. So we can define B to be X will go over script X of the compactification. So this will be the candidate for the compactification of the semi-abelian scheme, because we know, in general, the construction of Falkenstein does not give the universal semi-abelian scheme inside the compactification. But as long as there's some observation by, well, it's in Falkenstein, but also Vivek and Eno, that if you refine the polyhedral decomposition which produces the moduli, you can do so in such a way that the universal semi-abelian scheme is in fact plugged into the compactification. Then we should have some theory of logarithmic differentials here. But there are some points of the usual theory which do not work well. For instance, one thing that we need is that I won't extend it. There is an exact sequence where we know the surjectivity in the abelian case, and we do not know the surjectivity in general. Well, Cartier operator is not that good when you're working with something which is not smooth. There is the way to approach that by reflexive sheaves, but there are informations which are missing. So either the way is not that one, and we have to think about a good crystalline, a good cohomology in characteristic P to address that, and maybe inspire ourselves in Trian and Kato, or we have to read more about logarithmic geometry, and some information will come from that. So I'd like to, and well, actually I defined over there the P part of the weak Lefschetz defect. Thank you, merci beaucoup, obrigado.